Thank you all for coming to this very important encounter, one that's proven to be extremely useful for me and my profession, as well as my colleagues. I want to start by telling you that I have had the good fortune in the course of my career to work with scientists from all over the world. And I'm now honored to work with scientists engaged in the study of environmental Arctic change, or SEARCH. But some of my greatest teachers were indigenous hunters, starting with some 4 decades ago when I circumnavigated St. Lawrence Island in the northern Bering Sea with Alex Akia. Alex was a, sorry, I'm missing my advancing, here we go. Alex was a walrus hunter at Savunga. Some of you knew him. So Alex, Bud Fay, and I were studying a mysterious mass mortality of walruses in the Bering Strait region, and we visited carcass-strewn beaches all around St. Lawrence Island. So as we traveled in his walrus skin boat, Alex told me that the Yupik name for St. Lawrence Island is Savokak. The name, he said, refers to something that is shaped like a wrung-out rag. And indeed, that is the shape of the island. But Savokak is quite large. It's almost 100 miles across. And it's been occupied for over 2,000 years. So I asked Alex, how did your ancestors know the shape of the island all those years ago without benefit of aerial or satellite photographs? But it wasn't his teaching style to just answer directly. And so instead, he let me ponder this question for several days. So every day, as we made long passages in the skin boat, I pondered. And every evening in camp, I would advance my hypothesis of the day. I always got the same response from Alex, a slight smile and a shake of his head. Well, as I say, I learned a lot from Alex and his fellow hunters, and I have great respect for their teaching style. So I'm going to honor that style and let you ponder, at least for a few minutes, how his ancestors knew all those years ago the shape of their island. But I will take some pity, and I will give you a hint. And the hint is that it has to do with the albedo, or the differential reflectivity of surfaces. Well, those of you who were here last year may recall hearing another SEARCH scientist, Don Perovich, talk about the declining reflectivity of the planet as the area of sea ice diminishes. He explained that this diminishing albedo of the Arctic oceans and lands is a key amplifier of global warming. Snow, it turns out, is one of the most highly reflective natural materials on Earth. And as the area of land and sea covered by snow diminishes in the northern hemisphere, more heat is absorbed by the ocean, land, and atmosphere than is reflected back out to space. The impact is especially great in the Arctic Ocean. Enhanced surface warming melts sea ice, which further reduces the reflectivity, a self-perpetuating cycle. As a result, sea ice loss is contributing strongly to accelerated warming in the Arctic, where temperatures are now increasing at twice the rate of the global increase. We need to understand that these changes are unprecedented in the course of civilization. Our civilization evolved in the shadow, or maybe better said, in the reflection of a frozen Arctic. To see that, let's take a really quick look through the last 550 million years of our planet's history. So what you're going to see here is along the horizontal axis there is time. And so way over on your left, 550 million years ago, way over on the right, the present. And then on the vertical axis, I'm going to show you differences in temperature from the average over the last few decades. So the average is the 0 line, that blue line running across. So any temperatures above that were warmer than current averages, and temperatures below that are colder than that. So what's happened? Well, there have been times when the Earth was a lot warmer than it is now. And then it kind of cooled down, and then it went through a series of glacier cycles. And then, for the last few thousand years, we went into this rather odd period of rather stable temperatures. So to understand what that means to us, we have to kind of superimpose ourselves and some biology on this. So what was happening on the planet biologically over this period? Well, about 550 million years ago, fish evolved. About 450 million years ago, land plants first appeared. Then the dinosaurs came along, and then the mammals. But then we jump up to maybe 3 million years ago, relatively recently, relative to the evolution of fish, for example, and we start going into the glaciations and the beginning of an expansive sea ice cover. Humans didn't evolve from apes until 2 million years ago. And during these glacial cycles, polar bears diverged from grizzly bears. People don't arrive in Alaska until about 15,000 years ago. Agriculture wasn't invented until 10,000 years ago. And the Industrial Revolution is only a couple hundred years at best, okay? So let's expand this last period, this last 150-year period, and see what's gone on since then. Temperature-wise, we've continued to increase and increase the temperature, and that increase is proportional to the amount of greenhouse gases we're putting in the atmosphere. So we have to understand that where we grow food, the location of population centers, where the sea meets the land, all of this evolved in a context, in an environment dependent on a frozen Arctic. Hence, we have no precedents for dealing with this very rapid melting that is occurring. We need strong science to inform our responses. The scientific challenges include how people are and will continue to be impacted by ice melt and permafrost thaw, the main amplifiers of the warming induced by the greenhouse gases. So let's first look at some local impacts. Some of the most dramatic impacts for people in the Arctic stem directly from the declining sea ice cover. Oops, I'm going the wrong way here, sorry. When I first visited Sevokok in 1979, the area covered by sea ice in September averaged 3 million square miles. Since then, that cover has reduced by half. This loss of sea ice resulted in a warming signature equivalent to 25% of the warming caused by our emissions of greenhouse gases. So in a region of minimal roads, ports, and other infrastructure, humans, like Alex, depend on sea ice as an extension of land. They travel over that ice to access their marine foods. In the past few decades, however, an area of ice twice the size of Alaska has been lost, diminishing that access to food. Moreover, sea ice decline is outpacing model projections, suggesting that some key processes are not understood. But even the most optimistic models forecast a dire future for Arctic sea ice. The models make clear that unless we reduce considerably the burning of fossil fuels, summer sea ice in a few decades will be down to 1/8 of what it was when I traveled with Alex. We obviously need to accelerate our understanding and model development. Diminishing sea ice also threatens species that are dependent on sea ice as habitat, and in turn, it threatens people who are dependent on those species. Walruses and a host of other species are especially adapted to living on, in, and directly under sea ice. The much reduced ice cover of the near future may or may not be adequate to provide refuge for those ice-dependent species. Many of those species will be depleted, if not driven to extinction, by diminished sea ice cover. Walrus mortalities of the sort that Alex and I investigated are becoming more common as walruses are forced to coastlines by shrinking ice cover. But even those coastlines themselves are under assault. Reduced sea ice allows waves to batter shorelines. In northern Alaska, rates of coastal erosion have doubled in the last 50 years. The average rate of loss is now 5 feet per year, with some areas losing 65 feet per year. Homes, airports, oil wells, and ice cellars are being lost. Nor is the infrastructure damage limited to coasts. Permafrost underlies 1/4 of northern hemisphere landscapes. Thawing permafrost is altering landscapes and undermining infrastructure across the Arctic. So while diminished access to food, ecosystem changes, and collapsing infrastructure are impacting Arctic residents, people at lower latitudes increasingly will also feel the consequences of the changing Arctic. For example, permafrost thaw will impact people outside the Arctic by further amplifying atmospheric concentrations of greenhouse gases. So as the permafrost thaws, bacteria are able to mobilize carbon in the soil and emit it into the atmosphere. At current rates of warming, an additional 150 billion tons of permafrost carbon could be released during this century. So for perspective, that's equivalent to about 22 years of US emissions of carbon to the atmosphere at current rates. But of course, the global impacts are not limited to permafrost thaw. Since the year 2000, the volume of water annually entering the ocean from melting glaciers and ice sheets has increased by more than 500% in Greenland and almost 200% in the Gulf of Alaska. Projections of sea level rise this century range from 3 to 6 feet, depending on how much more carbon we emit and assumptions made about how the ice sheets will respond. In any event, millions of homes and billions of dollars in infrastructure will be imperiled. In contrast to land ice, sea ice does not directly influence sea level rise, but it does contribute indirectly through its amplification effect on atmospheric temperatures. And no location is immune to the changes in global weather patterns linked to the loss of sea ice in the Arctic. Increasingly persistent weather regimes are leading to longer and more severe droughts, cold outbreaks, heat waves, and wildfires. With larger portions of the Arctic Ocean becoming ice-free, ocean heat is escaping out of the Arctic Ocean and warming the Arctic atmosphere. One result is a reduced difference between the air temperatures in the Arctic and in the mid-latitudes. And that reduced difference is weakening the jet stream's west to east flows. These warmer, wavier jet streams are believed to be responsible for more frequent extreme weather events such as stormy winters and flooding in Europe, Asia, and North America, including on Svolkak in the northern Bering Sea. The people of Svolkak are experts at reading weather by reading the sky, and it is their keen sense of the sky that allowed them to discern, thousands of years ago, that the island is shaped like a twisted rag. So let me share Alex's full explanation. In the fall, the first snow on the island makes the island highly reflective. But before the surrounding ocean has frozen, it remains dark and absorbs more light than it reflects. When the cloud cover is just right in the interval between the first snowfall and the freeze up of the surrounding ocean, the island is reflected upwards and its shape is projected onto the cloud cover. Alex's ancestors recognized the projected image of a wrung-out rag was their home. Today, Arctic hunters, like their ancestors, rely on this differential albedo to discern where there might be open water. They looked for water sky, dark streaks on the cloud cover above ice capes to know where they will find open water and access to seals, walruses, and whales. So this same difference in albedo that allowed Alex's ancestors to map their home and to locate hunting areas, we now understand to be a key amplifier of global warming. So understanding albedo feedback is important, but we urgently need to understand the complexities of the whole Earth system. We need to harness our collective scientific knowledge and indigenous knowledge to meet a challenge unlike any civilization has previously faced. And SEARCH is working toward that end, but we need the help of everyone in this room, as you will hear in our first panel discussion this morning. Thank you.